you've got mail.
The problem at hand revolves around addressing the limitations of existing claw grabbers, which are commonly used by people with disabilities to access items in hard-to-reach places. Existing claw grabbers have shortcomings that include inadequate grip strength, extended force requirements, ergonomic issues, and limited versatility. Our goal is to design a device that extends the reach and improves the user experience for individuals with mobility issues.
Our mechanism consists of the claw, 4-bar linkage connected to the gears, and central rod. The central rod is then connected to the handle. When an input force of 30 newtons is applied, the spring in the handle is elongated, and the central gear is moved downward. The side gears are rotated, causing the links to move until the grabber claw is fully closed, or until the item is adequately gripped. When the handle is released, the spring compresses and stores potential energy. The links and grips are returned to the fully open position.
For our kinematic synthesis, the claw 4-bar linkage was the main focus. Based on our analysis and the use of the drawing perpendicular bisectors between 2 points, we established the nodal points and link lengths that would ensure a successful closure of the claw. The length of the claw grips is arbitrary. Applying the motion equations from the Norton Design and Machinery textbook, we generated the presented graph illustrating the relationship between handle and claw grip movements. The plot indicates that beyond a 4mm threshold, a 2mm handle adjustment results in an approximately 20mm claw displacement. This alignment with the design specifications demonstrates the attainment of maximum claw displacement with minimal users required handle movement. For the force analysis, we evaluated the reaction forces generated in the 4-bar claw linkage when a user applies a force of 30 newtons to the handle. By analyzing the relationship between the force applied to the handle and the reaction force of the claw in link 3, the mechanism's mechanical advantage can be determined for the open and closed positions. These are our force diagrams for the links, which we use for the equations. We solve those equations with matrix inversion. Following analysis, the open position exhibits a more substantial mechanical advantage compared to the closed one. This implies that users will exert less force to hold items with a larger width compared to a smaller one. Nevertheless, achieving the same claw grip on the object for both positions requires the user to apply a greater force to the handle. Ultimately, consumers will still benefit from reduced hand and finger movement when performing this task.
Link 3 encompasses the connection points between Link 3 and the claw jaws and the connection point between Link 2 and Link 3. This is because Link 3 translates the rotational force by exerting the side gears to horizontal displacement of the jaws, acting as the primary load-bearing component and translating the user's input force from the handle through the gripping action of the claws. We utilize SolidWorks FEA to determine the maximum stresses applied on Link 3. The following shows a mesh of Link 3 as well as the reaction forces applied across the 3 points on Link 3. The stress analysis simulation illustrations shown were used to determine maximum von Mises stresses used for factor of safety calculations. The following calculations show safety factors at 30 newtons applied load with cross-sectional area across which the stress is applied. High viscosity polycarbonate showcases the highest safety factor. The maximum ultimate and tensile stresses for the materials were sourced from mat web for room temperature 1-inch thickness. The following calculations show safety factors at 300 newtons applied load. High viscosity polycarbonate showcases the highest safety factor once again.